Section: Introduction. In this section, we delve into the iterative process of design refinement, where designers continuously improve their creations to strike a balance between aesthetics and functionality. While current multimodal generative models can automatically generate designs from text inputs, they often overlook the iterative guidance provided by human designers. Human design revisions involve complex changes that go beyond simple edits, such as exploring different visual elements and reorganizing layouts. These nuanced revisions are challenging to translate into clear instructions for generative models. Our goal is to leverage human revision edits to enhance multimodal generative models in layout design. We believe that the iterative and noisy nature of human design processes contains valuable insights that can improve generated layouts. To explore this, we have curated a new dataset called Rare Plus that captures how expert designers revise layouts created from specific text prompts. By incorporating human revision edits into the training of a Gemini backbone model, we aim to improve the quality of generated layouts. Our experiments show that models incorporating human revision edits outperform those that do not. Despite the noise in human edits, our best model achieves a design score close to human performance, surpassing a baseline model significantly. Additionally, we observe that models can benefit from early human guidance to avoid getting stuck in repetitive patterns during inference. This highlights the importance of human input in iterative design tasks. In summary, our contributions include introducing the Rare Plus dataset, demonstrating the benefits of incorporating human revision edits in training generative models, and comparing human-generated revisions with model-generated ones. We emphasize the potential of bridging the gap between human and model-generated guidance in layout design tasks. Section Summary. In this section, we explore the potential of leveraging human revision edits to enhance multimodal generative models in layout design. By curating a dataset capturing the iterative design process, we demonstrate the significant benefits of incorporating human revisions in training these models. Our research shows that human guidance surpasses model-generated edits, highlighting the importance of human input in improving the quality of generated layouts. Section: Task Formulation. In this section, we are given an initial user interface, UI, layout design S_0, and a language prompt T describing the UI's functionality. Our aim is to create an improved final version S_n that aligns with the functionality and meets designers' aesthetic standards. The human designer makes n revision edits from S_0 to S_n, resulting in intermediate layout states S_i, where i ranges from 0 to n. Each S_i can be represented by an image screenshot I_i and/or a sequence of design code C_i, depending on the model's capabilities. We focus on generating the final design code C_n based on the initial state S_0 and language prompt T. This differs from stateless generation like T, C_n or T, I_n. Our goal is to investigate how human revision edits impact generative models. We collected data using a Figma plugin to improve the outcome of a layout generative model. This dataset is 5 times larger than the original, with 5,500 training examples and 742 test instances. Human revision edits are often experimental and lengthy, involving hundreds of changes. We quantitatively measure the design affinity fluctuations across edit operations compared to the final design. Our modeling focuses on transitioning from an initial state to a later state, aiming to improve the design. We use a pre-trained Gemini 1.5 model and focus on input and output data variations. Our modeling paradigm centers on generating design code from multimodal features to evaluate layout images using FID scores. Section Summary. In this section, we aim to generate an improved final user interface, UI, layout design that aligns with a given language prompt and satisfies designers' aesthetic preferences. We focus on the conditional setup where the final design code is generated based on an initial UI layout state and a language prompt, differentiating from stateless generation approaches. Our study involves analyzing human revision edits' impact on generative models, utilizing a dataset collected through a Figma plugin that records design modifications made by professional UI designers to enhance the outcome of a layout generative model. Section: Direct Model. In this section, we start by considering the direct model as our baseline approach. The direct model takes any layout state in the revision sequence as input and directly generates the final design. We use an underlying generative model to train this process. Additionally, we explore a variant where a randomly sampled intermediate state from the revision sequence is taken as input. Next, we introduce the hop model, which models the iterative editing process through individual hops instead of treating revision edits as a one-step operation. We consider different sampling strategies for pairs of revision steps to capture the gradual improvement in design quality over time. Moving on to the single revision model, we investigate whether incorporating a human revision edit helps predict the final state. We sample intermediate layout states from the human revision trajectory to guide the learning process. In the multi-revision model, we incorporate more revision context by sampling a subset of layout states from the edit sequence. This richer form of guidance helps predict the final design state more accurately. We then discuss our experiments to evaluate the proposed model setups, focusing on how multimodal inputs are constructed, learning and inference details, and the impact of human guidance during testing. For the multimodal example construction, we formulate input examples as sequences of tokens, including text and visual elements. We use a natural language instruction to guide the pre-trained model on image and text co-reference. During supervised fine-tuning, the input sequence is fixed, and training only focuses on the output text tokens. In terms of training and evaluation, we apply the discussed model choices on top of GEMINI 1.5, using a smaller version with vision understanding capabilities. We fine-tune Gemini on our Rare Plus data and configure the context window size accordingly for different model variants. During decoding, we limit the number of tokens and adjust the temperature parameter as needed. Evaluation is done by rendering layouts as images and computing FID scores to assess the model performance. Section Summary. In this section, we explore different models for predicting final design states based on human revision sequences. We consider a direct model that generates final designs from layout states, a hop model that iteratively edits designs, a single revision model that incorporates human edits, and a multi-revision model that uses subsets of revision states for guidance. Our experiments evaluate these models on multimodal inputs and report their performance with and without human guidance. Section: Direct Inference. In this section, we will first explore how our model performs in direct inference. We aim to evaluate how well our model predicts a specific layout without considering how it was trained or any edits made during testing. If our model relies on edits during training, we duplicate the original layout to ensure that such cases are covered. The results are compared with the original rare results for reference. It's important to note that direct comparisons between Rare and Rare Plus may not be entirely fair due to differences in data sizes and evaluation sample sizes. To address this, we fine-tuned play on the Rare Plus dataset for fair comparisons. We observed a significant improvement in FID score when transitioning from Rare to Rare Plus on Play SFT, indicating the benefits of the new dataset. Additionally, there was a noticeable enhancement in FID score when moving from Play SFT to other results in the table after switching the backbone model to Gemini, despite having simpler model setups. When comparing different configurations within the same model type, we found that increasing the input variance generally leads to better FID scores, suggesting a positive relationship between revision edits and the final layout. For example, in the direct model, we replaced certain components to improve performance. The single, multi-revision models outperformed the direct models, while the quantized hop model performed the worst, possibly due to varying supervision targets across quantization buckets. In summary, incorporating edits during training improves performance at test time, even without providing these edits during testing. However, Using these intermediate edits as the training target does not yield the same performance boost. Interestingly, the single revision model performed the best, while the multi-revision model did not perform as well, likely due to confusion caused by longer edit contexts during training and testing. Moving on to human-guided inference, we investigated how human revision edits impact model performance. By feeding the single, multi-revision models with sampled human revision sequences during testing, we observed that incorporating single or multiple human edits improved the FID score. The model's performance approached that of experts, which is around an FID score of 6. In the next section, we will delve deeper into the behavior of the models in terms of their predictions. Section Summary. In this section, we evaluate our model's performance in direct inference, focusing on how it handles revision edits during training and testing. We observe that incorporating edits during training improves performance at test time, with the single revision model performing the best. Additionally, we explore how human revision edits impact model performance, showing that incorporating multiple human edits leads to significant improvements in FID scores compared to direct inference. Section: Iterative revision with human in the loop. In this section, we explored how involving humans in the iterative revision process can improve model performance. We tested a multi-revision model by first incorporating a human revision edit in round 1 and then allowing the model to revise itself. This setup mimics a scenario where humans correct model errors early on in the iterative process. The results, displayed in a table, clearly demonstrate the effectiveness of human edits over model-generated ones in the initial round. Human edits led to a significant improvement in the FID score from 23.2 to 17.1. Despite self-revision by the model, there was no substantial iterative enhancement observed. The best achievable outcome was capped at a FID score of 10.5 when incorporating a set of revision edits from humans. Bridging the gap from a FID score of 17.1 to 10.5 necessitates aligning human edits with model-generated ones, a challenge left for future research. Moving on to the question of whether models predominantly copy-paste previous revisions or engage in actual editing, we conducted a thorough analysis using 2 metrics. The first metric, denoted as ρ, measures the percentage of design code identical to the previous round. The second metric involves ROUGEL, where the model's output in one round is compared to the input in the subsequent round. Our analysis revealed that models do engage in editing the input layout design, with a low percentage of identical generations, ρ, and reasonable ROUGEL scores. However, beyond the first round, models tend to repeat themselves, leading to a sharp increase in ρ and near-perfect ROUGEL scores. Adjusting the decoding temperature helped reduce ρ and ROUGEL scores, but did not eliminate the repetitive trend. While addressing this echo chamber issue is not the primary focus of our paper, we highlight its significance and the potential for resolution. Lastly, we examined qualitative examples of model generation compared to the initial state and the ground truth. Our model tended to retain visual patterns from the input state, often repeating and extending existing patterns. In contrast, human edits, ground truth, resulted in more significant design changes, such as removing or replacing original patterns. Additional generated examples are provided in the appendix for further illustration.